All right, let's dive right into this explainer. Today, we're going to completely unpack the mechanical reality of how a decentralized, trustless financial network actually operates under the hood. We hear buzzwords like decentralized and peer-to-peer thrown around all the time, right? Well, today, we're looking at the actual plumbing. We're breaking down the Bitcoin Cash network not as some abstract pie-in-the-sky concept, but as a living, breathing mesh of computers.
Here is our roadmap for today. We'll start by looking at a network of equals. Check out the anatomy of a node, see how you actually join this P2P mesh, discuss the lightweight SPV solution, and finally wrap up with privacy in the mempool. Let's get right into it.
So the absolute bedrock of this entire system is the peer-to-peer network. When you send or receive Bitcoin Cash, there's absolutely no company, no bank, no central server acting as a middleman. Instead, your transaction is handed directly from node to node. It literally ripples across the network until every single participant has seen it. It's just a completely self-sustaining global mesh.
Starting off with Section 1, a network of equals.
To really grasp this, we have to look at its flat topology. The absolutely crucial thing to understand here is that there are no boss nodes. None. Every single participating computer is a peer. They're all technically equal, providing and consuming network services at the exact same time. It's built entirely on reciprocity, you see. There's zero hierarchy here. Just like the very early days of the internet, this flat architecture is totally by design. It is literally the only way to maintain complete decentralization of control. Because think about it, if you introduce a hierarchy, you instantly introduce a central point of failure, and we definitely don't want that.
Moving on to Section 2, the anatomy of a node.
So every node in the system is built from 4 potential building blocks. You've got the wallet function, the miner function, the full blockchain database, and the network routing function. Now pay close attention to that network routing function. Every single node in the system absolutely must include it just to participate. I mean, you have to be able to talk to the network, validate, and propagate data, right? But those other 3, they're actually entirely optional.
And what's super fascinating about this is how these functions essentially act like Lego bricks. You can mix and match them based entirely on what you need to do. So a full node runs all 4, for total independence. That's the pure experience. But looking at the other options, a solo miner just runs the routing, blockchain, and miner blocks. An edge router, like maybe for a massive cryptocurrency exchange, might just run the routing and blockchain functions. And a lightweight SPV wallet, it just runs the wallet and routing blocks, totally skipping the massive blockchain download.
Now, if you were to run a full node today, you'd most likely use the Bitcoin Cash node, or BCN software. This is the reference implementation that's most commonly run by miners. And honestly, the beauty of it is just how accessible it is. You can run this thing on completely ordinary hardware, literally even a tiny little Raspberry Pi. It communicates with its peers out on the network using port 8333, and it features an interface on port 8332 for other software to interact with it. Just a quick heads up though, the network has a scheduled, hard-coded upgrade every May. So node operators absolutely have to keep their software updated so they don't get left behind.
All right, Section 3, joining the P2P mesh.
So imagine you just booted up a brand new node. It's totally blank. With no central server, how on earth does it know who to talk to? Well, it all starts with DNS seeds. Your software actually ships with the names of a few highly reliable servers hard-coded right in, usually around 5 of them. Your node queries these seeds and they return a list of random active IP addresses of other nodes currently on the network. It's basically a simple directory service just to get the newcomer bootstrapped and introduced to the crowd.
Okay, so once your node has an IP address, it basically knocks on the door and initiates a handshake. First, Node A sends a version message describing itself, stuff like its software version, its current block height, and protocol. Node B receives that and replies with a VERAC, which is just shorthand for version acknowledgement. Then Node B turns around and sends its own version message, and Node A replies with a VERAC. And it's only after this incredibly polite little introduction is complete that normal operation actually begins.
But here's the catch. If you're a full node, you have a lot of catching up to do. You're starting with only the hard-coded Genesis block, and you have to download hundreds of gigabytes of history. That's a massive amount of data. Nodes handle this by first comparing their block heights. Then, using inventory signals, they basically ask the network, hey, who has the longest chain here? Once they figure out exactly what they're missing, they send highly precise get data requests. And they're smart about it too. They spread these requests across multiple peers, so they don't just completely overwhelm a single connection while downloading all those gigabytes.
Let's move right into Section 4, the lightweight SVV solution.
Now, downloading hundreds of gigabytes is totally fine if you're running a PC, but what if you're running a wallet on your smartphone?
I mean, your phone definitely can't handle that kind of massive data load, right? This brings us to Simplified Payment Verification, or SPV. These SPV nodes skip the bulky transaction payload completely and only download the block headers. Guys, this literally strips the data down by a factor of 1,000. It creates a highly portable, super lightweight node that's absolutely perfect for mobile phones and resource-constrained devices. It lets you participate in the network without needing to go out and buy a massive external hard drive.
But that begs the question, how does it actually know a transaction is valid without seeing the whole history? Well, instead of combing through the entire chain's history for double spends the way a full node does, an SPV node simply asks a peer for a compact cryptographic proof. It's called a Merkle path. It then verifies that path against the block header. Basically, it's just checking how deep a block is buried. It completely trusts that the network's collective computing power, the proof of work acting as building blocks on top of it, serves as a highly reliable proxy for validity.
Of course, there is a trade-off here. While they are highly secure in practice, SPV nodes don't see every single transaction, which means they are theoretically vulnerable to what's called a Sybil attack. That basically means an attacker could surround your SPV node with fake nodes that just feed it lies. The defense against this is simple but absolutely crucial. An SPV node must connect to several random nodes to ensure diversity. If it connects to even just one honest node, the fake data is instantly exposed. But yeah, for infallible, pure security, nothing beats running a full node.
And finally, Section 5, Privacy and the Mempool. We are zooming all the way down to the microscopic data layers now. Think about this for a second. If an SPV node doesn't have the whole blockchain, it has to constantly ask its peers for specific transactions related to its own wallet. But if you're constantly doing that, how do you avoid doxing your identity to anyone who might be monitoring the network? Because if you ask for exact addresses, suddenly everyone knows exactly what you own.
The incredibly clever solution to this is called a Bloom filter. Think of it like this. Imagine you're a tourist. Instead of asking a local for directions to your exact hotel at 23 Church Street, which obviously reveals exactly where you're staying, you instead ask for directions to any street ending in RCH. It's a fuzzy probabilistic match. On the network, this 16-bit array hashes your addresses into a pattern. A positive match is just a maybe, but a negative match is a definitely not. This brilliant little trick guarantees you never miss your transactions, but completely hides your true addresses in this thick cloud of false positives. It's really elegant.
So once a transaction is actually broadcast out into the wild, where does it go before a miner eventually puts it in a block? It goes straight to the mempool. The mempool is a temporary list stored entirely in a node's RAM. When you open your phone wallet and you see a payment marked as unconfirmed, you are looking directly at a transaction just sitting in the mempool, waiting patiently for its permanent home in the blockchain.
These transactions propagate across the nodes like an expanding ripple in a pond. But because of normal network latency, sometimes a transaction arrives out of order. A child transaction might actually show up before its parent. Now, instead of just outright rejecting it, the node puts the child in an orphan pool. Once the parent finally arrives, the orphan gets instantly promoted back into the mempool. It all cascades and organizes itself just beautifully, completely without any central coordinator managing the queue. It's the absolute definition of emergent network consensus.
When you step back and look at the whole picture, from that flat topology to the intricate handshakes, right down to the Bloom filters and the mempool, it results in this incredibly resilient, permissionless mesh where value flows directly from peer to peer. Everything works together in perfect harmony to create this self-organizing, mathematically secured ecosystem.
As we wrap up this explainer, I really want to leave you with a thought to chew on. We've spent all this time looking at the mechanical reality of how these nodes communicate and secure data. When value can flow globally, securely, and completely seamlessly without any central authority or single point of failure, how does that reshape the future of our global infrastructure? Thank you so much for learning with me today. Keep asking those big questions, and I'll see you in the next one.